Assalamualaikum. Hi everyone, I'm Cikgu Niswan. Hess's law states that the enthalpy change for a chemical reaction is the same, regardless of whether the reaction occurs in one step or a few steps. At the end of this video, you should be able to state Hess's law and its used to find enthalpy changes that cannot be determined directly. And you should be able to calculate enthalpy changes from energy cycles.
Alright students, let's say we want to determine enthalpy change in a reaction A to C. As we can see here, the reaction can occur in one stage using a direct route from A to C. It also can occur in two stages from A to B to C, where B is the intermediate stage. By Hess's law, this delta H equals to delta H1 plus delta H2. Actually, Hess's law is used to determine enthalpy changes that cannot be found by direct experiments. Example, it is impossible to measure directly the enthalpy of formation of carbon monoxide. However, we can determine the enthalpy changes for the following reactions. So, how can Hess's law determine the standard enthalpy formation of carbon monoxide?
There are two methods to apply Hess's law. Here we're still using the reaction between carbon and oxygen gas. How do you cycle to work out an enthalpy change of this reaction? Basic ideas are, first, we need to identify the same starting point and the end point of the cycle for all reaction routes involved. Why? Hess's law states that the enthalpy change for any chemical reaction is independent of the route provided the starting conditions and final conditions, reactants and products are the same. Alright, this is direct route or route 1. If excess oxygen is used, the heat liberated is 393.5 kJ per mole when 1 mole of carbon is changed directly into 1 mole of carbon dioxide. Whereas this way is route 2, where 2 steps needed in formation of carbon dioxide. In step 1, 1 mole of carbon is burned in limited supply of oxygen to produce carbon monoxide. So, this is standard enthalpy formation of carbon monoxide we want to determine, right? In step 2, 1 mole of carbon monoxide obtained in step 1 is burned in excess oxygen to produce carbon dioxide. 283.0 kJ per mole of heat is liberated. Mathematically, by applying Hess's law, we can determine value of standard enthalpy change formation of carbon monoxide is negative 110.5 kJ per mole. Alright. Method 2 is algebraic method. Basically, using this method, the enthalpy changes for each individual reaction during the process are added together like this. We will discuss this in details later. Now, we will see how algebraic method can be used to determine standard enthalpy formation of carbon monoxide. The wanted equation is when 1 mole carbon react with half mole of oxygen to produce carbon monoxide. We are given such information here. First, rearrange each balance equation with reactants and products on the correct side. Example, our wanted product is carbon monoxide gas. Thus, we have to reverse this equation into this one. If you reverse a chemical equation like this, the sign of the enthalpy term also change, or we must multiply the given delta H by -1. Then, add the rearranged equations together to give the overall equation for the reaction and add the delta H values for all these equations to calculate delta H for the overall reaction. Enthalpy or energy level diagram also is very useful for application of Hess's law. There are simple recommended rules to be followed when drawing energy level diagrams. Always start from the zero energy level, that is elements in its normal physical state. Example, carbon must be in solid and oxygen is gas. For negative delta H values are shown using arrows pointing downwards, showing decrease in energy, while positive delta H values are shown using pointing upwards, showing increase in energy. Each level should indicate only one type of enthalpy change. We can now see that the combustion of carbon via the direct one-step pathway or via the indirect two-step pathway results in the same carbon dioxide gas product and releases exactly the same amount of energy per mole of carbon dioxide gas produced. Thus, Hess's law is proven. Okay, students, still talking about enthalpy cycle method. There are two types enthalpy cycles that can be used to calculate standard enthalpy change of any reaction. Look at these two cycles. The most difficult part of applying Hess's law is drawing the cycle with the correct label, arrows pointing in the correct direction. Tips. For both cycles, first, we need to identify the starting point and the end point. Starting point must have two arrows starting here. End point must have two arrows point to it. Be alert that combustion cycle and formation cycle have different direction of starting point and end point. Now, look at this past year question. We are given enthalpy formation data, so we should use formation cycle. Remember, start with determine the starting point and end point for formation cycle. From the enthalpy cycle drawn, we can see by applying the Hess's law, root 1 equal to root 2, where root 2 consists of two stages. This shows that sum of standard enthalpy formation of products equal to the sum of standard enthalpy formation of reactant plus standard enthalpy reaction, where standard enthalpy reaction here refers to as standard enthalpy combustion of propane. Remember, when multiplying a thermochemical equation by factor n, multiply the delta H value by the same factor. So, mathematically, we can solve value of standard enthalpy combustion of propane is negative 1938 kJ per mole. Now, look at this question. You are given enthalpy combustion data and you are required to determine standard enthalpy formation, also means standard enthalpy reaction of glucose. Thus, we can use combustion cycle. Okay, students, look at these two enthalpy cycles. Make a comparison. What can you see? Yes, in first cycle, the oxygen atoms are balanced to fulfill the law of conservation of mass, where matter cannot be created or destroyed by physical or chemical change. In the second enthalpy cycle, it is not applied. There is a tip. When using standard enthalpy changer of combustion, it is not necessary to balance the oxygen. These are definition of standard enthalpy of combustion of glucose and definition for standard enthalpy of formation of carbon dioxide and water. That's all for today, students. See you in the next section. Bye!